Hello, folks. We just went over the basics of radioactivity. Now, in this video, we're going to start to look at the decay process as a whole and the speed behind this radioactive decay. So, let's go ahead and get started. The idea here is that radioactive decay occurs under a very regular pattern, regardless of the decay method, whether it's alpha, beta, gamma, positron, electron capture. It's a very regular pattern because, unless we're doing some sort of outside nuclear transmutation, this is always a first order process. The nucleus shakes itself unstable and it falls apart. So this means this occurs at a constant time interval. A constant time interval where it's like it takes that essentially for a given sample, after a certain period of time, exactly half of the material will have undergone decay, regardless of what we have. This is, of course, the half-life. We discussed this previously. But that is kind of a advantage and major disadvantage of nuclear chemistry. So if you have a half-life of 2 years, 1 gram would decay to a half a gram after 2 years. After the 4th year, it would be down to a quarter of a gram. After the 6th year, it would be down to 0.125 grams, and so on and so forth. 8 years, it'd be even smaller, but it doesn't just go away. It's always by half. So as the likelihood of this decaying is just the material has to have enough energy to shake itself apart. And the likelihood of any given molecule of shaking itself apart is based on this first order process. Now, each element, regardless of its decay pattern, will have a different half-life. So each radioactive element will take different times to decay. So you have a mixture of elements. They're all radioactive. Some will be decaying faster, some will be decaying slower, and you can use that and figure out ratios between them if we know about them. So this is advantage because it is a good way of measuring time. Because it's impossible to really speed up or change the natural rate of this decay, there's no chemical reaction you can do that makes this go faster. And because these decay rates are very constant and very well known and very well measured, we can use this as essentially a clock. The basic carbon dating uses this. That nitrogen is typically 714 in the atmosphere. Atomic number 7, mass number 14. That by absorbing cosmic rays, essentially positron rays from the sun, I guess that'd be beta rays from the sun, it converts the nitrogens into carbon-14. This carbon-14 then undergoes a series of reactions to eventually form into carbon dioxide and carbon-14, carbon dioxide. Plants breathe in that carbon-14, carbon dioxide, and incorporate that into their cells. Plants then get eaten by animals, and this carbon-14 gets incorporated into their cells, and it just builds its way up the chain. Now, while this carbon-14 does decay, it is a very slow process. And based on the rate, there is a more or less constant ratio of carbon-14 in the environment compared to carbon-12 and carbon-13. It's very trace, but it is well known. And when essentially we can measure and compare how much carbon-12 to how much carbon-14 we expect to see. and that's going to be constantly being built up. So as it's decaying, it's more or less being incorporated as it's decaying. So once we've lived long enough and it reaches equilibrium, it's essentially it's going to stay constant until a subject dies. So when the plant gets died, killed, or cut down and turned into something like wood beam that gets put and built in a Viking longship, or gets cut down its cotton cloth and gets woven into a tapestry, or it's in a human, a woolly mammoth, and it gets frozen in the ice, or in a human as a mummy gets preserved and stored in a sarcophagus, that it's no longer absorbing any carbon-14. So it cannot keep its ratio the same anymore, and it now starts to gradually decrease. Well, the half-life of carbon-14 is something like 5,700 years. So it takes 5,700 years for this ratio to go down by half. Well, if we can measure the amount of carbon-14 that's left, we can back calculate the age of an object. Now, keep in mind we're measuring trace quantities of carbon-14. And so once we get down to enough half-lives, the accuracy is going to go way down, because we're trying to measure traces of fractions of carbon-14 that's left. So when an object becomes older than 50,000 years old, it's really hard to measure these tiny changes in carbon-14. So now the same process we use to measure age of a living organic organism, we can use to measure the age of rocks. If we find a uranium deposit in the earth, we can then measure how old this deposit is based on the amount of uranium to the amount of lead-206. As I said in the last video, lead-206 is not naturally occurring lead. It only occurs in uranium deposits from the special decay process. By measuring the how much uranium-206 there is versus how much uranium there is, how much lead-206 for uranium, we can measure essentially how old is this rock. And this is the way we can approximate the age of the Earth based on the age of these rocks. But so calculating the rate, if you're just doing a first order differential rate law, its rate is equal to a K constant times N, which N is just the number of radioactive nuclei. You can treat it like a concentration. But since it's often better to use this to measure time, we're going to use an integrated rate law. That the natural log of N after some period of time over the N initial, N at time 0, is equal to negative K times the time T. So this is just like what we saw back in chapter 14. And with that in mind, we also saw in chapter 14 the easy way to measure K is related to the half-life. The half-life is just ln2 over T1 half is equal to K. So we can figure that out. If we know the half-life, we know K. If we know K, we know the half-life. But just looking at this, 500 kilogram drum of uranium-238 stored for 1 billion years. 1 billion is 10 to the 9th years. How much uranium is left after that time? If it helps, the half-life is 4.5 times 10 to the 9th years. How long would it take us to get down to 1 kilogram? Third is 1,000, 10 to the 6th is 1,000,000. So this helps us put this. Uranium-238 is a very slow process. So the first thing is, what's our K? Our K is going to be Ln2 over 4.5 times 10 to the ninth. So Ln2 divided by 4.5 times 10 power of 9. So K is something like a really small number, and that's fine. 1.54 times 10 to the negative 10th. Well, ln of n sub t, 500 kilograms, equals negative 1.54 times 10 to the 10th, 10 to the negative 10th, times 1 times 10 to the ninth. So just a billion years. We're storing this for just a mere billion years. Times negative 1. Okay, so that's this side. Now I'm going to take the inverse log to the inverse log. So inverse log so that I can get this ratio. Multiply by 500 to get t. And I have, how much is left? After a billion years in storage, 428.6 kilograms left. The majority's left. After a billion years of storage, this is decayed. We've lost not even like 72 kilograms. Not even 72 kilograms. So a lot of it's left. How long would it take to get to 1 kilogram? So let's remath it. We still got our K. So ln of 1 over 500 equals negative 1.54 e to the negative 10th times t. So let's figure this out. Ln of 1 over 500. We're going to divide by negative 1.54, 10 root negative 10. It's going to be 40, about maybe 40.4 billion years. About 40 billion years to get this down to 1 kilogram remaining. And now you know why. And now you know why storing this is kind of a bit of a problem, because it takes a lot of forethought, a lot of time investment to let this decay. I mean, in all fairness, you're not just leaving uranium-238 hanging around. You're not trying to just dispose of uranium-238. You might store it, you might find some use for it, but right now you're not just storing that around. But that's why 40 billion years, it's still going to be around after all of humankind, essentially. That's why it's still around. 500 kilograms, still hanging around. Now, nuclear reactions, you can see why it's a lot of this problem is it's such a problem, because you have to think in the long term. But transmutation is another thing we can do. This is the one way you could actually speed up or slow down a nuclear reaction, by transmuting one radioactive element into another. You can create new, heavier elements through collisions with high-speed atoms. You could use this new collisions to then cleave them into smaller atoms as well. But so particle accelerators like the relativistic heavy ion collider or the Large Hadron Collider are capable of speeding up protons to near the speed of light. And once they slam into heavy atoms, they can potentially be absorbed into them and generate new radioactive elements. Atom smashers like this are ways we get certain elements used for cancer treatments, like cobalt-60. So that's not the common form of cobalt, but it's a radioactive form of cobalt. Right? We can generate all synthetic elements above 92 by using these atom smashers. But some of them are so radioactive they only hang around for less than a second, and you have to basically pick up the pieces and see, oh, we see these different radioactive compounds, and you look at what has formed after you slam these guys together and use that to go, oh, we created a new element, and then it immediately decayed and broke into these new elements. And so that's kind of like work your way backwards to pick up the pieces to prove, oh, I formed this. But this little this is where we're going to leave you here, but here's this basic idea. Okay, when I hit nitrogen with a gamma particle, I'm going to form a carbon, and what other particle? What other particle? So I'm going to hit it with a gamma, 14 carbon. If I slam an alpha particle into a silicon, silicon is, of course, 14. And americium, if you let americium naturally decay, americium is element. Americium 95. It's going to decay down into gamma and neptunium and what else? Okay. So this is where we're going to leave you, but we'll work this out real quick. So, look, 14, 14. 14 plus 0 is going to have to also be 0. 7, 0, 6, and what? It has to be 1. The particle that has 0 and 1 is a positron emission. After this converts, we have a positron emission to form carbon-14. Combining these together, atom smashing alpha particle into a silicon, this forms 16, and 28 plus 4 is 32. This 16 is, I think, a sulfur atom. Yes, it's a sulfur atom. And americium, a 237 plus 0 plus what is 241. Well, I'm missing 4. Okay. 93 plus 0 plus what is going to be 95. That's 2. So americium undergoes alpha decay and a gamma decay to form neptunium. So just more practice math. So that's where I'm going to leave you today. It's a really short video, but on the last video we're going to talk more about radiation and the energy of nuclear power and other things. So have a good day.